Alright, so today's lab we're going to do simple pendulum and vector lab where we're going to do addition of vectors to calculate equilibrium in the systems. So for the simple pendulum lab, we're going to measure the period, which I use tau, at 5 different heights and 5 different lengths I should say, and you're going to do 4 trials at each length. And I use tau, and the reason I use tau, I'm not sure what your textbook uses at this point in time, but at some point in time, if it's P for period or T, you will shed that because for the most part, T is reserved for thermodynamics, temperature, and P is pressure. So tau has been around since Kepler's laws, and eventually a period of oscillation will become tau, as far as you know as engineers. So what you're going to do is you're going to measure the period at 5 different heights, and I have written less than half a degree, or less than 10 degree drop angle. And so what you want to do is set up the pendulum and measure out the height. Now, as in the last experiments, you do not need to measure the exact height that I have written up there. All right, you just need to measure the exact height that you have measured out, okay? So if you try to measure it out to 0.10 and you get 0.09, you can use that value. You don't have to sit there and finick with this to try to get it perfect. You just have to make sure you record the value that you're using, all right, because it's going to affect your answer. All right, you'll set it up so the pendulum is initially, or so the bob is initially dead center, and most of your boxes are already set up, but it should say time, pendulum. I'm going to raise this to an angle of roughly 10 degrees, and then I'm going to hit the black key to start, release, and you'll hear 3 beeps. Beep once when it goes through, starts the timer, comes to the top. Beeps a second time when it goes through to measure the period of 1/2 an oscillation, and then goes to the top over here, and then beeps again to measure a full oscillation. So the time that it measures on here is the exact time of the period of oscillation. Heights. So once you measure the period at those heights, you're going to make, I didn't write it up here this time, but you're going to make your table like you did last time with the free fall. So you'll have each of the heights, and then you'll have the times, T1, T2 through T4, because there's 4 trials, and then you'll have an average time, tau, and then you'll have an average tau squared. Okay, and we'll graph those. You want to graph them length versus tau squared like this, with length on the y-axis and tau squared on the x-axis. Then I want a rough estimate of the slope, and what does it represent? So just like before when you calculated the slope for free fall, and then you determined that the slope should be equal to g over 2. In this particular case, you're going to do the same thing by giving me a rough estimate of the slope before you leave, and then you look at the equations. You have L on the y-axis, and you have tau squared on the x-axis, and you know that if it's linear, which it should be, y is equal to mx plus b, where b is the y-intercept. The y-intercept should be 0. If you don't believe me, lower it to a height of 0 and see how long it takes to oscillate. It should be 0 seconds. So that cancels. Then your y is length, and your x is tau squared. And you have a formula over here with both those variables in here. So just like last time, only a little bit trickier, you're going to rearrange this equation to make it look in this form. And when you do that, whatever's left over, whatever junk is left over, should be the value of the slope that you record experimentally. Okay? So yeah, once you find the slope and you find out what it represents, you do a percent error on those 2 values. Remember, only 2 values that you're comparing. For class, I ask you to get the slope by just measuring rise over run for maybe a couple points and giving me an estimate. For your lab reports, and from now on for both sides, you will do a linear fit and you'll do a trend line. So you'll pop out a box when you do your linear fit, and it'll tell you the slope of that line. And that's the slope I want you to use on your lab report when you compare percent error. Okay? So if you don't know how to do that, look it up, but it's literally once you do your trend line, there's a box at the top, and it'll pop out the equation for the line of best fit. Then the last step before you leave is to draw the diagram that I have already drawn for you, and then solve for F restore and F tension. So if you look at the pendulum, this is a diagram of the pendulum at a given theta when it's out to the side. When I release it, there's a tension force, which is equal and opposite of this force. And there's a restoring force which brings it back to center. All right? I'll give you a hint. One of them is mg sine theta, and one of them is mg cosine theta. You can guess the right answer, but I'm going to make you justify why it is that answer. Okay? Now here's the trick. There's two ways to do it. Mathematically and with logic. All right, and that's something you might find interesting as I go around the room. I'll explain to you. But there are two different ways to prove which one is mg sine theta and which one is mg cosine theta. Is anybody here in differential equations? Okay, I'll give you another hint. It involves initial conditions. So look at the situation and think about initial conditions. Bonus question, how does the period tau depend on theta? All right, the answer is not, it does not depend on theta because of this formula not having theta in it, okay? Something happens in this formula, given the parameters of this experiment, that allows me to cancel theta out of it, okay? And if you further justification, just think about it logically, or think about it with a little experiment. If I measure the time for tau, I'll probably get a value. If I measure a time here, oops. If I measure the time from here, I probably get close to the same value of tau. So at those two thetas, nothing changes. What happens if I drop it from here? Is that the same tau? All right, fair enough. What happens if I drop it from here? Is that the same tau? So we're in agreement that at some theta, this fails. All right, that's a little hint to your bonus question as to what I'm looking for. So the point of this lab is to solve and determine equilibrium for each configuration based on this pulley system. So we have this table, and it's called the force table. And the whole purpose of the force table is to balance three different pulleys in equilibrium, all right? Each of these pulleys can be representative of a vector, all right? So when we're balancing vectors, you would say one force plus another force is equal to another force, all right? So if I pull in this direction and someone else pulls in this direction, in theory, there's someone who can pull in the opposite direction to a point where the rope between the three of us is stabilized dead center, right? At that point, we'd all be in equilibrium. All right, so the objective is we're gonna put the first two vectors that I have labeled up there, we are gonna put the configuration, we're gonna set the configuration identical on your force table and then solve for the resultant vector, both experimentally and then mathematically. All right, so in the first case, we have 0 degrees, and I'll move the pulley to 90 degrees. And the masses should be, I got 100, so 50 on one and 50 on the other. So it should be 100 and 100. Remember the hanger weighs 50 grams, has 50 gram mass. So once I've done that, now I'll show you. I can find an equilibrium configuration for this system with my hand by just simply picking this string up and moving it to an angle and providing a force. So we know there's some angle and there's some force that I can give in order to have this ring suspend dead center and not touch the pin. All right, that's how you know it'll be in equilibrium. So you can do it one of two ways. You can solve mathematically first, or you can solve experimentally first and then determine after mathematically. Your experimental results should be rounded out values because you only have certain increments of weights on your tables. So I don't expect to see an experimental result that says 169.45 grams. Where'd you get the 0.45 grams, right? It's going to be some rounded out number like 170. But once you find the equilibrium position experimentally by putting masses on here and determining what angle it needs to be, you can then solve mathematically up here by using the laws of vector addition. So what do we know? Here's the formulas over here. We know that the sum of the y components has to be equal to 0 and the sum of the x components equals 0 in the whole situation. The way I kind of relate this is if I have somebody tug on a rope and they walk a certain amount east and south, okay, and I have somebody tug on a rope and they walk a certain amount east and north, all right, I have to obviously go in some configuration west and either north or south, all right? But I can figure this out by breaking it down and saying how far did they go east and how hard are they pulling south, how hard are they pulling east, how hard are they pulling north, adding those two numbers together and then figuring out the resultant on the other side and then calculating the force that I need. So in the first case, we'll work through it. The initial vector V1 is at 0 degrees and 100 grams. All right, so what is x1? Well, the x1 component, it's pointing straight down the x-axis. There is no y component because it's not any direction in y. So the entire x1 component is 100 grams. Okay, what is y1? Well, it's not pointing in the y direction at all, so there's a 0 y component. y1. Now look at this vector. What is x2 in this case? It's pointing directly up the y-axis. What is x2? 0, right, because it's not. And then what is y2? 100 grams, very good. So, we have our vectors now. We have our x and y components, and we have the formula: the sum of the y's equals 0, sum of the x's equals 0. So, just to show you up here, that means that x1 plus x2 plus x3 equals 0, and because of that, x3 is equal to a minus x1 plus x2, right? Which is really simple in this case. It's just 100, which means x3 is minus 100 in the x direction. So you want to do this on your lab notebook. Draw your vector for your x3 and draw it minus 100 to the best scale you can. Then, by the same logic, y3 is equal to a minus y1 plus y2, okay? And because it's 100, it'll be minus 100. So you can draw it here, but one of the things you know about vectors, or you've heard at some point in time that actually applies now, is that a vector can be moved tail to tip, perpendicular or parallel to its position, right? You've heard this before at some point? Which means I could take this vector and slide it over here, and I'll draw it just like this, okay? I know this is 100, and I know this is 100, and this makes up a triangle, and that's the right angle right there. So now I need to know what is the magnitude of the resultant vector, and to solve for the magnitude of this, you use Pythagorean theorem: a squared plus b squared is equal to c squared. All right, so it's 100 squared plus 100 squared is equal to c squared, and you should find theoretically that this is like 141 point, I don't know, something. So it's about 141. I'm pretty much doing the first one for you. Now, to find the angle, theta, well, there's a couple ways you can do it, but the best way I do it is, this is theta right here, and you have this equation for tan theta is equal to opposite over adjacent. So you can arctan opposite over adjacent, or inverse tan this function on the right hand side, and it will give you the angle theta. So it's 100 over 100, so the inverse tan minus 1 of 100 over 100, which is just 1, is equal to theta. And I can tell you right now, the arctan of 1 is 45 degrees. So it's 45 degrees, and it's in our third quadrant, okay? So this is 180 degrees, and this is 45 degrees, which means that the resultant angle right here is 225 degrees. So the resultant vector mathematically is 141 point, I got it backwards, but 141 point dot dot dot, and the angle is 225 degrees. Okay, that is your V3 theoretically, and experimentally you'll write down whatever you find by using your balance table. Okay? All right, really quickly, looking at the second one. Now you have a case where you have to decompose it. It's not as easy as the first one because your first vector and second vector were solely the components. In this case, you have to break it down into triangles. So let's look at V1, and I'll just do V1 really quick for you. If I draw a line straight down, we know that's a right angle. This angle right here, 70 degrees. Okay? So, I need to figure out the y component, and the y component is on the opposite side. So I use sine theta is equal to opposite over hypotenuse, and the hypotenuse is the magnitude, which is 120. So 120 sine theta, sine of 70, is equal to the y component, and 120 cosine theta, or cosine 70, is equal to the x component. So that would be y1 and x1. So there, you solve for your y1 and your x1. Same thing with this triangle, or this vector. You want to break it down into triangles, and then this angle right here, I guess, would be 20 degrees. And solve for the x2 and the y2, right? Once you get those values, sum them together, take the negative of them, and draw your resultant vectors out the other side, and then just do what I did here. Use Pythagorean theorem to figure out the magnitude, and use tan theta to figure out what angle it's at, okay? And you'll do the same thing for experiment number 3, and That's pretty much it. There is no percent error for this lab, and the reason for that is because it doesn't really make much sense to say percent error for the lab. The only thing limiting your error is the fact that you don't have the right increments. So you can calculate theoretically what the value should be, and then you know exactly what it should be, but you don't have those increments. So just write down how close you can get, and write down the experimental error.